Let's dive right in. We're going to tackle the absolute chaos of AI terminology. If you've ever felt like you're just drowning in a sea of acronyms and buzzwords, then this is for you. We're going to build a simple, clear structure to make sense of all of it.
I mean, does the world of AI feel a little bit like this sometimes? Just 1,000 terms flying all over the place. Everyone's talking about RAG and agents and embeddings and guardrails, and you're just kind of supposed to nod along like you know exactly how it all fits together. It's a total alphabet soup. And yeah, it can be pretty overwhelming.
So that's the big question, right? How do we bring some actual order to this chaos? What if there was a way to organize all these concepts so we could see not just what they are, but how they all relate to each other?
All right, so here's the idea. Our solution is an AI periodic table. Now, I know, think back to chemistry class. The periodic table isn't just some boring list of elements, right? It organizes them, it groups them by their properties, and it helps you predict how they'll react with each other. And that is exactly what we're going to do for AI. Now look, full disclosure, this isn't some official industry-wide standard, but it is an incredibly powerful mental model that'll help you decode pretty much any AI system you ever come across.
So this is our blank canvas, a simple 4x5 grid. This is the framework we're going to use to map out the entire landscape. Everything from the most basic, fundamental building blocks all the way up to the most complex systems.
Let's start with the rows. You can think of these as levels of complexity. At the very top, row 1, we have our primitives. These are the absolute fundamentals, the atomic units of AI. You can't break them down any further. Then in row 2, we get compositions. And that's where we start combining those basic elements into something more useful. Row 3 is all about deployment. These are the concepts you see in real, actual production-level systems. And finally, row 4 is emerging. That's the really exciting, cutting-edge stuff that's still taking shape as we speak.
Okay, now for the columns. We're going to call these families, because they group our elements by what they do, by their function. So starting on the left, group 1 is the reactive family. These are things that react directly to some kind of input. Group 2 is retrieval, which is all about searching in memory. Group 3, right there in the middle, is orchestration. Think of this as the conductor of the orchestra, the thing that coordinates all the other pieces. Group 4 is validation, which is absolutely crucial for safety and accuracy. And then finally, all the way on the right, Group 5 is for the models themselves, the powerful engines that make everything go.
All right, our framework is set, so now it's time to meet the elements. Let's start filling in this table.
So let's start with row 1, the primitives. These are the absolute basics. First, over in the reactive family, we have P for prompt. A prompt is the simplest thing you can do. It's just the input you give an AI. It's atomic. Next, in retrieval, is M for embeddings. Now this is a really key concept. Embeddings are how you turn words and concepts into math, into lists of numbers, so that an AI can understand and search for information. And finally, way over on the right in the models family is LG for large language models. You can think of these as kind of like the noble gases of our table. They're stable, they're foundational, and they're the engines everything else is built on. And really, that's it for the primitives. In a way, everything that follows is just a clever combination of these three things.
Now let's move up to row 2, the compositions. And honestly, these 5 concepts right here power most of the AI systems that you interact with today. So in the reactive family, we've got func for function calling. This is where an LLM can actually reach out and use an external tool, like, say, asking a weather API for the current forecast. Over in retrieval, we have vex for vector databases. Remember all those embeddings we just talked about? Well, you got to store them somewhere, and that's what these are for. Smack in the middle, under orchestration, is RG for RAG, or retrieval-augmented generation, and we'll dig into that one in just a sec. Then, to keep things safe, we have GRA for guardrails in the validation family. And finally, in models, we've got MM for multimodal models, which are the ones that can understand not just text, but images, audio, you name it.
Okay, let's zoom in on RAG, because it's a term you hear absolutely everywhere. As you can see from our table, it's an orchestration process. This is the key. The AI doesn't just make stuff up. It goes and retrieves relevant facts from your documents first, and then it generates an answer based on those facts. This is so crucial for grounding AI in reality and stopping it from hallucinating.
Now, row 3 is all about deployment. This is about putting AI into production, into the real world. Here we find AG for agents, which you'll see are a major evolution of function calling. In retrieval, we have FT for fine-tuning, which is how you adapt a general-purpose model to a very specific set of data. For orchestration, there's FW for frameworks, things like LangChain that help you tie all these different pieces together. In validation, we have RT for red teaming, where you literally try to break the AI to find its flaws before someone else does. And finally, in the models group, we have SM for small models, which are becoming a huge deal because they're specialized, fast, and way cheaper to run. And if you look at that first column, you can really see the evolution of the concept of agents. It makes so much sense. You start with the simple prompt, which is just direct control. Then you level up to function calling, which is a specific, predefined action. But agents are all about autonomy. An agent uses this think, act, observe loop, where it plans out steps, uses its tools to take action, and then sees what happens, adjusting its plan until it achieves its goal. It's a massive step forward.
And here it is, the full picture. Our final row, emerging, is where things get really, really interesting. We have MAW for multi-agent systems, where you have different AIs working together on a complex task. SYN for synthetic data, which is when you use one AI to generate training data for another AI. Wild, right? Over in validation, we've got IN for interpretability, which is the huge challenge of understanding why a model makes the decisions it does. And finally, THA for thinking models, which are models specifically designed to reason through a problem before blurting out an answer. And hey, notice that gap in orchestration? That's the frontier. For now, it's an open question what brand new element will emerge to fill that spot.
So we have our table. But the real power here isn't just knowing what the elements are. It's seeing how they combine to create reactions. Exactly. This is the whole payoff. Now we can use this table to actually understand how real-world AI applications are built piece by piece. So let's walk through the most common AI pattern in business today, a chatbot that knows all of your company's internal documents. Okay, so first, you use embeddings to turn all your docs into vectors. Then, you store those in a vector database. When a user asks a question, RAG, our orchestrator, goes and retrieves the right chunk of information. That info then gets stuffed into the prompt, which is sent to the large language model to generate a grounded answer. And of course, any smart company is going to wrap the whole thing in guardrails for safety. See? We just combined 6 different elements from our table to build something incredibly useful. Okay, here's another reaction, the agentic loop. This is where things get really dynamic. You give the AI a goal, right? Something like, book a flight to Tokyo for under $800. The agent is the brain here. It breaks that goal down into steps. To actually do those steps, like search flight APIs or check your calendar, it uses function calling. The agent then observes the results of that action and decides what to do next, looping back and forth in that think, act, observe cycle until, boom, the goal is met.
So, the most important point here is that this isn't just some theoretical exercise. You can actually use this table. It's a practical decoder for any AI you come across.
Seriously, try this. The next time you see a new AI product demo or read a press release, run this little checklist in your head. First, identify the elements. What building blocks from our table are they actually using? Second, map the reaction. How are all those pieces connected and in what order? And third, and this one's really important, try to spot what might be missing. Are they conveniently forgetting to mention a safety element like guardrails? Are they using a massive, expensive thinking model when a simple, small one would do the job? This helps you cut right through the hype. And that's really the power of this whole thing. It gives you a framework. It's a way to categorize and connect all of those crazy terms we saw at the beginning, and finally transform all that chaos into clarity. So I'll leave you with this final thought. You know, the periodic table for chemistry has stood the test of time. It's fundamental. So is this the start of something similar for AI? I mean, what do you think? Will we see a version of this hanging on school classroom walls one day? It's a pretty interesting question to think about.